We present a new glasses-free 3D display technology. Our display consists of multiple disjoint attenuation layers that are illuminated with a uniform light source. This design is very similar to conventional LCD-based systems, but instead of presenting a single target image, we compute a stack of patterns that synthesize a virtual 3D scene, or, alternatively, a high-contrast 2D image. We show that the problem of determining the attenuation patterns necessary to display a 3D scene can be formulated as that of a computerized tomographic reconstruction. In this formulation, every view of the light field encoding the scene corresponds to an orthographic projection of the attenuation medium. The reconstruction determines the patterns that recreate all views of the desired light field in the best possible way. While traditional tomography aims at reconstructing a physical attenuation volume from measured projections, for instance in medical imaging, we synthetically create the desired observations and compute attenuation patterns that do not necessarily correspond to any familiar object shapes. To verify our theory, we have built a display prototype that consists of a transparency stack with clear acrylic spacers in between the individual layers. The prototype shows a variety of 2D and 3D example scenes. Unlike other volumetric displays, our approach enables the display of objects outside the boundary of the physical device. It supports occlusion, motion parallax, specularities, and translucencies for a range of vantage points both horizontally and vertically about the display. We show how an increasing number of disjoint layers increases the quality of 3D scenes and the contrast of 2D images. In our paper, we derived the upper limits of all attenuation-based displays for an arbitrary number of layers and show that more layers increase the sharpness of objects inside and outside the display. It is well known that multiple stacked attenuators increase the contrast of a displayed image. However, there has been no practical algorithm to determine the patterns that need to be shown on disjoint layers to create a desired 2D HDR image. We show that the optimal patterns confirm existing heuristics for dual layer architectures and provide the first extension to multiple disjoint layers. Conventional parallax barrier displays, here simulated with a limited contrast, can show arbitrary images, such as numbers, to different viewing directions. When attempting to display such a scene at the highest possible resolution, our algorithm fails in this case. At the same subsampling rate and display thickness of parallax barriers, however, it performs equally well. Lenslet-based displays have been successful in displaying 3D content for over a century. This approach, however, reduces the spatial resolution of any displayed image by a fixed amount. Parallax barrier systems make the same resolution trade-off. The advantage of such displays is that the barriers in programmable LCDs, for instance, can be switched to transparent, thereby enabling a high-resolution 2D mode. This technology is employed in the upcoming Nintendo 3DS. Unfortunately, parallax barriers are very dim. Our approach displays bright, high-resolution imagery with a high contrast and could provide the key technology for glasses-free 3D displays of the future.